All right, so I want you to label your notes Doppler effect. And the way that I like to think of the Doppler effect is I like to imagine, so imagine this scene, right? Imagine like a calm day on the pond. God, what are you wearing? All right. So anyway, so imagine a calm day, the pond in the middle of the forest on a calm day, right? No breeze, just everything's calm. The water is perfectly flat. And then imagine that you're a bug, and you know the bug can like jump on top of the water. So imagine you're a bug, you're just floating there in the middle of the pond, right? And then you're just enjoying the nice weather, and then you just start to jump like this. So jump, jump, jump like this. So what's going to happen? Waves. You're going to make ripples, right, going out from you. And we're going to say that you're jumping at, we're going to say a frequency of 1 hertz. So what I want to do is I want to imagine, again, you're right here. So this is you, you're a bug, right here in the middle of the pond. And as you jump at 1 hertz, these ripples go out from you in these concentric circles. We're going to say that because you're the one making these waves, I'm going to label you as S. The S means the source. You are the source of the waves, right? And now imagine that your friend is, you didn't notice that anyone's there. You thought you were by yourself. That's why you were jumping. But your friend was right here. Okay. So you're here just minding your own business, and you're just going jump, 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 1 hertz, 1 time per second, right? Your friend is sitting here minding his own business, but what's going to happen as the waves come? You're going to go every time that the ripple gets you, right? And so we're going to call your friend, we're going to label your friend O, and the O means observer, the S means source. So S means source, O means observer. Now, if you, so the frequency of the source, right? The frequency that you were jumping up and down was 1 hertz, right? So that was the frequency of the jumps, right? What is the frequency of the over here, right? When the wave gets you and go, what's that frequency? Yes, I'm giving you the scientific term. Right over here, you're jumping at 1 meter per second, making ripples. And over here, your friend is getting, what frequency is your friend bobbing? Yeah, 1 hertz. It's the same, right? So we're going to say in this case, the frequency of the observer is 1 hertz, right? Okay. That's basic, right? That's one idea here, right? Are you paying attention to your physics? Yeah, that's 1 hertz. You get 1 hertz. Okay. Okay. So now you notice that your friend's over there, right? And you decide to go over and say hi to your friend. And the way you do this is you decide to go jump, jump, jump. Still 1 hertz, right? But now you're jumping this way closer to your friend, right? So what's going to happen is that's right. Yeah. So I'm going to jump 3 times, right? Jump 3 times this way. What's going to happen? Well, that last, let me draw myself again. So that last ripple is going to be centered along where you are now. But the second to last ripple is going to be centered back here, right? And the third to last ripple is going to be right there. I'm not very good at drawing these circles, but this is kind of what the ripples are going to look like, right? So you are still the source of the ripples, and you are still jumping at 1 hertz. But the question is, your friend, the observer, now how is your friend going to perceive the ripple, right? So you're jumping this way at 1 hertz, right? But your friend, what is the frequency of the bubbles, right? Is it going to be greater than, less than, or equal to 1 hertz? Greater than, right? The waves are going to get there more often. So we're going to say that the observed frequency is bigger than 1 hertz, just for the sake of argument. Let's just say it's 2 hertz, right? This is the Doppler effect, right? The Doppler effect is the idea that that the frequency changes if something is coming toward you or if something's going away from you, right? You imagine if you were over here, what frequency would you hear? Bigger or smaller than or equal to 1 hertz? If you're on this side, your frequency would be, it wouldn't be equal. It would actually be longer because these are farther apart, right? So now think about, again, the race car, right? When a race car passes you, what do you hear? You hear, meow, right? Why? Because when the race car is coming towards you, you hear a higher pitch, right? When the race car goes away from you, you're over here, you would hear a lower pitch, right? Okay, so let me show you, I want to show you some of the animation. So that's the drawing, but I want to show you some animations of this real quick. I know. Are you really? Is it carb day next weekend? Is it carb day next weekend?
There's just a race. My dad is taking us. I don't know. He's asking for one to go.
Nice. Doppler effect. We're going to start with this one. So what I got here, let me.
Does that ring a bell at all? When you asked if I wanted to go to a race. Okay. The Indians don't want to make all about cars, not me.
Why can't I?
What is it? May 30th. Oh, that's my birthday.
All right, so here's what we got here, right? So this is an animation of what I was talking about. I know it's hard to see. Let me turn off the light so it's easier to see. Right, so this is the animation of what I was talking about. So you've got a bug here. I'll run it again. Right, you got a bug here just jumping on the water. You see the ripples are coming out. They're coming out at some certain frequency, right? But if instead I make this bug, let's see, I go forward at 2 meters per second, right? You can see that as that bug jumps, right, the waves in front of the bug end up closer together. The waves behind the bug end up farther apart. That's what's happening, right? So I got another animation here that's interesting. This is from the perspective of a plane, right? So again, you have a plane. If you had a plane that could hover, which it can't, but if you have a plane that could hover, you would have something looking like this. But again, if you got a plane that's moving forward, again, the sound waves get bunched up in front of the plane and they get spread out behind the plane. Now, here's what I want to think about, though, because sound waves are not ripples on a pond, right? Ripples on a pond are a way to think about it. So ripples on a pond are a good way of thinking about it, but ripples on a pond are not sound waves, right? What kind of wave are a sound wave again? Longitudinal, which means what do each of these lines represent? So you can use them to think about frequency, but when we think about a wave, right? So transverse waves have crests and troughs. What do longitudinal waves have? What do you call them? A push. You remember what that was called? Or with a C? Compressions. So sound waves have compressions and rarefactions, right? The idea is each of these lines it represents a compression. So what happens is the sound wave sounds like a higher pitch because those compressions are closer together. Yes. Okay, so that's the next thing, right? So the question then becomes, what if I get going faster and faster, right? So here I'm going 85% of the speed of sound. So look what's happening here, right? Remember these compressions. This is an area where the air is literally compressed together. And if I start approaching the speed of light, I get to a point where all these compressions are compressed close to each other. Speed of sound, right? Yes.
How are you going to speed of light?
My bad. Speed of sound, right? As you get close to the speed of sound, these compressions are all right next to each other. And again, they're physically next to each other.
You can actually see that happen.
Yes, and you know what we call this? This is the sound barrier right here. Right now, we haven't broken it yet, but we are.
I thought you were talking about the white cone.
Well, we'll get there. 1 second.
Can we
Yeah.
break the sound barrier?
Right. Yes, we can. But what we're doing here is we are making a sound barrier, right? What a sound barrier is, it's a physical thing, right? It's the air has physically been compressed. All those compressions are compressed next to each other so that you get like really thick air that you have to break through, right? So this is a sound barrier. Let me actually show you when you're at the speed of sound. So here I'm at the speed of sound. So you can see that I'm compressing all that air in front of me and I'm making a physical sound barrier. And then what's going to happen is once you quote break the sound barrier, right? So once you're going faster than the speed of sound, let me go a little bit faster so it's easier to see. So you can kind of see how you are now staying in front of the sound waves. But there's something else that's really interesting about this, because if you look at these here, right? This here is, again, a bunch of compressions that are all lined up. And if all the compressions are lined up, what kind of interference is that? Constructive interference, right? All these compressions are lined up. They're constructively interfering, right? So you're making a really big wave. What do we call that wave? Really big wave? Not a tsunami. What? It's the sonic boom, right? This is the sonic boom, right? The sonic boom is you have all these compressions who are now next to each other. So a sonic boom is actually there's the sonic boom, which you actually hear, but then you can also sometimes feel if you're like if there's a low flying plane that's broken the sound barrier, you can actually feel a shock wave.
Your eardrum explode.
If you're close enough. Oh yeah.
If a low flying plane versus
Oh really?
anybody like right underneath the barrier.
Fair enough. And then I guess that makes sense to me looking at this. But yeah.
So what's a plane versus sound barrier? Would it be more aerodynamic?
That's a really good question. Yes, it's harder. Because the sound barrier is a physical thing, it's harder to, once you break the sound barrier, it's easier to keep going faster, right? You have to spend more energy to get from just prior to the speed of sound to just over the speed of sound than you do to increase your energy after that.
How much over have we gone?
I'm sure that Mach 3 at least that's 3 times. But 900 meters per second. I'd have to do it. I'm going to show you a video in a second. I think they're going to quote it for you. Yeah. No, I did it. Okay. It was a project I wanted to see if it was working. All right. Let me show you this video about sonic booms. Let me make sure, because I'm sharing this. I want to make sure that I'm sharing. What? Video unavailable?
Reload it.
I just did. Okay. This is it. I must have moved it. All right, we're good.
Sound travels at about 760 miles per hour, or 340 meters per second. That's about 661 knots on an average day at sea level. And sometimes you can almost see it. Going close to that speed through air can cause some unusual visual effects. What you're looking at here is a NASA image of an SR-71 bending light waves from the pressure differentials it's producing. Air's pressure and temperature both drop when airspeed increases. Rapid changes in density can be enough to bend light like a lens. How does it happen? Airspeed increases as it flows over the form of an aircraft, pushing its way near Mach 1, the speed of sound. That means that even aircraft slower than the speed of sound can accelerate the air moving over them beyond the speed of sound. As pressure all around the aircraft drops, that air cools, and as air cools, its ability to hold moisture drops. So if there's enough moisture, you'll see it form in clouds that appear attached to the aircraft itself.
Oh, I haven't. No.
Cone-shaped clouds you see aren't in fact traveling with the aircraft. Each section of air is spontaneously reacting to the temperature and pressure change induced by the aircraft's body sliding past. Then there are the shock waves. Shock waves are formed by the air that can't get out of the way fast enough, forming a pressure wave. We perceive that pressure wave as sound. Aircraft actually usually produce two booms. They just reach us so quickly in succession that we can't distinguish the two. All of these factors are quite normal and have come to be expected in images that capture supersonic, transonic, or even near supersonic flight. But on rare occasions, we do get a glimpse of something special. At Kennedy Space Center on February 11, 2010, an Atlas rocket launched into ideal conditions for showing off shockwave. And this is the result.
See that? I think they're going to show it. If you missed it, they're going to show it again.
We hope you've enjoyed this little tour of visual and auditory speed of sound phenomena. Visit avweb.com for aviation news and inside information for pilots.
There it is. Yeah.
This has been Glenn Pugh for avweb.com. Thanks for watching.
Yeah. Yes. Now you'll notice, like, well, so this was kind of Gavin's question. Like, you need a lot of you need a lot of energy to break through that actual barrier. So when planes are designed, a lot of times they've got a really sharp corner. Sometimes you'll even see they've got like a point on the end that sticks out, and that's kind of to help break it. What's that?
Like a bird.
I guess. Yeah.
I don't think birds are
Okay,
Now, oh, and we talked about, I think Sam brought this up when we were talking about waves. Like the crack of a whip. The crack of a whip is actually a whip breaking the sound barrier. Yeah. Okay.
The speed of sound is 767.269 miles an hour.
So 800 miles per hour. So Mach 3 would be what? 2400.
It's speed of sound.
So it'd be 2400 about.
Yeah. It's 2300. And yeah.
All right. So, any questions about this Doppler effect? Sonic booms. All right.
So if I throw an orange at like 800 miles per hour, is it gonna like annihilate anything?
No, I mean, like, so what you're talking about is essentially a bullet, right? If you throw a gun is essentially just throwing a bullet fast enough that it will hurt something. But yeah, you could get something that would throw an orange that fast. Yeah.
How fast is the bullet?
I'm not sure.
Depends on the size
Yeah.
of the bullet.
You know, I had just thought about that right before you you said that. I don't think that that's a sonic boom. Yeah, that's the question. I don't know how fast it makes them go, but I think it's like hundreds of miles per hour. I don't think it's thousands of miles per hour. So I don't think that it's breaking down there.
It's kind of a bullet.
Yes.
So I looked up to like 2,600 feet per second, which is 1,800 miles an hour.
Oh, so that would be
Yeah.
twice the speed of sound. Okay,
So bullets break the sound wave.
I guess so.
Yeah, but they don't have enough mass. They don't have enough drag.
That's a fair point.
How
Yeah.
much mass
Okay.
is the race
They
going to
how light can do it. Got so much drag.
So you've got this, you've got way more volume of air
Right.
that is doing the boom. So you might have a sonic boom. Okay, yeah, you might have a sonic boom, but there's not enough volume of air, like volume in terms of amount of air to get volume in here. Yeah, that makes sense. Yeah. Well, but I think what Braden's saying is that the problem is that the bullet itself is not, it's not that it's not going fast enough, it's that it's not big enough. That, like, yes, there is a sonic boom, but it's not gonna be loud. It's not really gonna be a boom.
What's the fastest?
Well, we were just talking about in an airplane, you can go Mach 3.
It said the world record is Mach 6.7.
Mach 6.7, so that's 6.7 times the speed of light.
5,140 miles an hour.
Who did that?
Someone, William J.
All right. What I want to do next is I want to talk about how you can solve problems with the Doppler effect. So, by the way, when I say Doppler effect, just to be clear, this is what I'm talking about, right? So
This beachfront Verbo is about to become part of an unforgettable vacation memory.
What does it mean when a jet breaks
this is not.
and after the car passes, the pitch you
Right. So listen as it passes. You've heard that before, right? How it goes lower pitch once it's passing. Okay. So, all right. So what I want to do here is I want to come up with an equation for the Doppler effect. And this is what we're going to say. So the frequency you hear. The frequency you hear is going to be equal to the frequency of the source. Now, this is the equation is a little bit complicated, but I'll explain in a second. So just write it down to begin with. So it's going to be V. Give me 1 second. I got to make sure. I know it's plus minus, and I think that I got to double check to make sure that I'm not doing this backwards. Yeah, okay. V plus minus VO on the top. And then on the bottom, it's going to be V, and it's got to be minus plus VS on the bottom. So this is the equation. Just write it down, and I'm going to show you what it means here in a second. I'll show you why in a second. Yeah, so it has to be plus minus on the top, and it has to be minus plus on the bottom. Yes, the order is important. I'll show you how in a second. So I want to define these terms. So when I say F is going to be the observed frequency, whereas Fs is going to be the source frequency. And then we've got three different velocities. We have V, VO, and VS. V with no subscript is going to mean the speed of sound. VO is going to mean the speed of the observer. And VS is going to mean the speed of the source. And then as far as the plus and minuses go, right? So we're going to have to, there are some times where we're going to use plus, there's sometimes we're going to use minus. And here's what we're going to say about that. So whenever objects are traveling toward, you're going to use the top sign. Whenever objects are traveling away from each other, you're going to use the bottom sign. All right. I'm going to hand out a practice problem. Why are you saying thanks question mark? I know, she said like, she said thanks, like she didn't think that it was a compliment. All right. So read that, read question number 1 here. And we're going to do this, we're going to do one together. You are at a train station in London getting ready to go out of the country to see grandparents. You are walking at a slow pace of ½ meter per second, and the train, which is stationary, is producing a whistle of 1070 hertz. As you walk towards it, what will the frequency will you hear from the whistle? Right? Okay, so let's do this. You can call this the 5-7 assignment. So I always start, and I know that you will roll your eyes when I say picture, but I really think that a sketch of what's going on is really helpful in these situations. The sketch doesn't have to be like super detailed, but what I want to be clear is here's the train, here's me going towards the train, right, at 0.5 meters per second. And the train is making a whistle of 1070 hertz. It's just helpful to keep all of this organized in this way. It makes you less organized. Now, the other thing in your picture that I want you to include is which thing is the source here? The train is the source of the sound, and you are the observer, right? So I'm going to label source and observer. All right. See if you can set up some knowns and unknowns. Oh, good question. Speed of sound. You need that. Speed of sound in air is 343 meters per second. And I will always give that in. You don't have to memorize that. Sorry. It's 340, not 343. I'm sorry. What? It's stationary.
Oh.
So take a look at those definitions of the knowns and unknowns and tell your partner what you think they are in this case, as many as you can get. All right, Aiden, you want to give me a known or unknown for this?
For traveling.
Yeah, what symbol would you call that?
That would be the speed of, like the speed of the observer.
Yeah, so it's VO. So that's why it's helpful to decide which is your source and observer and put it on your picture. All right, Chloe, what else? Yeah, and what should I call that? F or FS? FS, because it's the source frequency. Okay. Connor, anything else? No. Anybody else have anything else? Go ahead, Maddox. So speed of sound, which is we're going to be regular V. It's going to be 340. There's one other thing we know. Yeah, Max. Source is 0, it's stationary. Yep. Now here's what I usually do. When I have a velocity of the observer and the velocity of the source, I usually like to indicate whether it's toward or away. So in this case, the observer is going toward. The source, it doesn't matter whether you say it's toward or away because it's 0, right? Or going toward something or away from something at 0 is the same. But let's look at what happens when I put it in the equation. So plug into the equation, F equals Fs, V plus minus VO, V minus plus Vs. So what I want to show you is what do you do with the plus minus and the minus plus? Well, the key here is the observer is going toward. So if the observer is going toward, that means we're going to use the top sign. That's what we said back here, right? If you're going toward, you use the top sign. But what I'm going to do is, in this case, I'm going to use the top sign up here for the observer. I'll probably just go ahead and use the top sign on the bottom as well. But the source, if you do minus 0 or plus 0, it's the same. So when I plug this in, I get something like frequency equals 1070 times quantity 340 plus 0.5 divided by 340 minus 0. And you can put that in your calculator. I would like everyone to go ahead and try putting it in your calculator because I want to make sure you got to be careful, make sure you follow order of operations correctly. So, yes. Yeah. And so first of all, I got 1071.6. Questions about that? And yeah, and Olivia's right. We got to put a unit with it, so it's hertz. So this is a frequency that we hear. Now let's ask, does this make sense? Why does it make sense?
You're not that far.
You're not that far from him, that's true. But it's stationary and you're going toward. And so if you're going toward, right, just like a car is coming toward you, think about the race car, right? Is it high pitched when it's coming towards you or low pitched? High pitched. Is my pitch higher if I'm going towards? Yes. So that means that I probably did it right. See what you can do with part B.
Would 1070 still be FS?
Yes, FS is still 1070, yes. So is it going toward or away from each other? That means it's the top side. Well, no, this one's plus minus, that's fine. Yeah, please be careful. The equation, the top thing on the equation is plus minus, the bottom one is minus plus.
So wait, the VF is the U, right?
No, the source is what's making the sound. Train. Correct, that's FS. And then TS would be the speed of the train.
Oh, VO is V.
VO is, you're the observer, you're observing frequency. What I got. Because they're going toward each other and the top side. Remember, toward the top. Yes. Well, so now what's happening is the train's going this way, you're going this way, right? So you're trying towards the train, but the train's going away from you. All right, I want to do C because C is just a little bit different in terms of the coordinate ways. So read through that, and again, I'm really going to encourage you to think through like what the picture looks like at C. Like just a very simple sketch of who's chasing who in which direction. I think it'll help you determine who's going forward, who's going away.
So whenever you do any problem like this, you have to determine what the frequency is when it's stationary, when the object is stationary.
You would have to know one of the frequencies.
Okay.
So I could ask you, I hear this, what was the frequency of the source? But yeah, usually we'll give you the source frequency. Yes.
What would someone?
All right. All right, yes, thank you. So the reason why I think it's helpful to have a picture here is because if you look at this, right? So I think we can agree that the velocity of the source is 22 and the velocity of the observer is 11.1. But are these toward or away? Are they both away? No, the source is going away from you, but the observer is running toward the source, right? So when I do this, right, you got to be very careful because you got to say, okay, the source is going away. So away means bottom sign for the source. VO toward is a top sign. So in this case, they're both going to end up being plus. What? Oh, thank you. Good call. Thank you. I think this is going to be the last one we'll do. Can somebody check me on this number? Yeah.
I got 10. Yeah.
Say again. You know what I've done? I put my numbers in the wrong spot. This was an example of what not to do.
I like how I contemplate it.
Yeah. Okay, so the observer is 11.1. Okay. And somebody, I think somebody said this, right? My answer doesn't even make any sense because on average, right, this thing's moving away from you, which means we should end up with we should be end up at the end, right? We should end up with a lower number. So what if it's 351.1 divided by 362? 1037.8.